All right, welcome everybody. So in this video, we are going to continue working with our orthogonal projections. And in this case, I want to start by thinking about how we can project a vector y, which is sitting in Rn, onto a subspace W of Rn. So if we have a subspace W of Rn, these are going to be things like lines through the origin, planes that contain the origin, and so on. And so as we're working with our vectors and matrices, we'll take a look at examples in data science really shortly, and we'll see that this decomposition is really the central component of doing what is called linear regression. So when we say that we are going to decompose a vector y into two vectors, one of them is y hat, that's what we'll call this, the other being z. Then the picture is we have a subspace over here, W, and here's our vector y that is sitting in, both of these are sitting in Rn. And so this vector y has an orthogonal projection, so it has some component to this vector which is parallel to the subspace W, which sits in the subspace W, and then there's a second component that we call z, which is exactly orthogonal to the subspace W. So when I take y hat, which is this vector in W, and add to it the vector z, that puts me right here at y. So this component y hat we call the orthogonal projection of y onto the subspace W, and this is sometimes denoted with this notation, projection of y onto W. And then the component of y, which is orthogonal to W, that's what we call this piece z. And once I figure out what y hat is, then z is the missing piece that I need to add to y hat in order to get back our initial vector. So normally, once we find y hat, we find z by taking the initial vector y and subtracting the orthogonal projection y hat. And we've discussed how we can construct these orthogonal projections. And so the theorem that we can state to find these orthogonal projections is what's called the orthogonal decomposition theorem. So in general, if W is a subspace of Rn, then each vector y in Rn can be written uniquely in the form that y is equal to y hat plus z, where again this y hat is in W and this vector z is orthogonal to every vector in W. So then if U1, U2, all the way up to UP is a subspace, an orthogonal basis, for this subspace W. So that means U1 and U2, the dot product of these two vectors would be 0. And the dot product of U1 with all of the vectors in this set are 0 other than itself. U2 dotted with all vectors in this basis besides itself would be 0. So using this orthogonal basis, it's really convenient because this gives us a nice formula for finding the weights that we need for each of these orthogonal vectors in our basis, so that when we take that linear combination of basis elements from this orthogonal basis, we get y hat. We get the orthogonal projection of y onto W. And that formula for each of these weights, so for vector ui in this basis, we find the weight ci by taking the original vector y, inner product with ui, divided by the inner product of ui with itself. And if we have a basis for W which is not orthogonal, then this formula does not hold. And we've also seen that if, in addition, we happen to choose an orthonormal basis, so each of these vectors has a magnitude of 1, has a length of 1, then this formula gets even simpler because these denominators are going to all equal 1. And in that case, the weights are just the inner product of y with ui. So let's take a look at an example on the next slide to show how we can find a formula for an orthogonal projection and the component which is orthogonal to that subspace W.